You're listening to a production of the National Media Archive. To learn more or volunteer, go to nationalmediaarchive.com.
Imagine you're in the middle of a lively game of catch. The ball rockets towards you, and in a split second, you know exactly how to move your hand for a perfect grab. How? What's really happening under the hood? Your eyes measure the ball's speed and size. Those two technical terms, velocity and visual acuity, come into play. The data's collected instantly, and your brain gets to work. Now you might be thinking, is my brain some kind of supercomputer? In a way, yes. Information flows from your eyes to your brain and back to your hand, all thanks to a network of neurons. Let me tell you a story. Once, during a baseball match, I caught a ball I barely saw. My conscious mind didn't have time to process, but my brain and neurons did the heavy lifting in milliseconds. That's the magic of neural signaling, your body's built-in electrical grid, allowing you to react faster than you can even think. So, how does your body send messages so fast? Enter the neurona specialized cell, acting as both messenger and gatekeeper. Neurons transmit information as electrical signals, technically called action potentials. Think of action potentials as digital pulses, like a telegraph system from the old days. Now, here's the conflict. You're exposed to a barrage of sensory data every second: sounds, sights, touches. How does your brain avoid overload? Well, neurons filter and prioritize these signals, ensuring only important messages like a fast-approaching ball or a sharp pin underfoot make it to your muscles for action. Without this neural superhighway, you couldn't react to danger or enjoy your favorite song. It's the difference between missing a catch and making a game-winning play. Let's zoom in. What exactly happens when you see something? Light enters your eye, strikes the retina, and is converted into electrical signals. These signals travel through the optic nervea bundle of axons, which are like thick electrical cables right into your brain's visual cortex. Here comes a challenge. The brain must decode this burst of electrical activity instantly, turning it into a mental image. Imagine the optic nerve as a high-speed internet cable, carrying data, packets, action, potential at incredible speed. This rapid-fire communication is why you can dodge a flying frisbee or spot a familiar face in a crowd. The efficiency is mind-blowing. Let's break down a neuron's anatomy. Picture a tree. The neuron's dendrites are the branches receiving incoming signals from other cells. The cell body, or soma, is the trunk processing the input. Then, the axona long, singular branch sends the message onward, like a relay baton in a race. Here's a key technical term. Synapse, the tiny gap between neurons, where neurotransmitters jump across to carry the message. But how does the signal know where to go? The axon uses electrical impulses, ensuring messages travel in one direction only. Think of it as a chain of domino sensei. The first one falls, the sequence is set, carrying the signal from dendrite to axon to the next cell. Before a neuron fires, it's in a state called the resting potential. What does that mean? Imagine a battery loaded with potential energy, just waiting for you to flip the switch. This resting potential is due to a difference in electrical charge, about 70 millivolts between the inside and outside of the cell membrane. Technical term alert: electrochemical gradient. It's the combined force of electrical and chemical differences that keeps the neuron poised for action. Now, you might ask, if the neuron is at rest, how does it spring into action so fast? That's the magic of ion channels, tiny protein gates that can open or close in response to voltage changes. So, with this delicate balance, your neurons are like sprinters on the starting blocks, ready to explode into action when needed. Here's a puzzle. Why do neurons sometimes ignore weak signals but respond explosively to others? The answer lies in the threshold potential. A neuron needs to be excited past a certain point, about 55 millivolts, before it will fire. This is called the threshold, like pushing a button hard enough to click. And here's the tricky part. Action potentials follow the all or none principle. The nerve impulse is always the same size, no matter how big the stimulus, as long as it crosses the threshold. It's digital, not analog like flipping a light switch. Either the light turns on, or it doesn't. No in between. This ensures your nervous system sends clear, reliable signals crucial for fast reflexes and precise control of movement. Let's dive into the fireworks show inside your neurons when a signal is sent. It starts with depolarization. Sodium ion channels open and positive ions rush in. The inside of the neuron flips from negative to positive, creating an electrical spike. That's your action potential, zipping down the axon. But then comes the reversal, repolarization. Potassium channels open, letting positive ions flow out, restoring the negative interior. Technical terms in action. Depolarization is the positive charge wave, while repolarization resets the neuron, readying it for the next signal. Think of it as charging and discharging a camera flash quick, powerful, and ready for the next shot. Ever wonder how your nerves avoid sending mixed signals? After firing, the neuron actually overshoots, becoming even more negative than at rest. This is called hyperpolarization. During this time, the neuron enters the refractory periota short phase where it absolutely can't fire again no matter what. Why does this matter? Imagine if your car's engine could start again before it actually stopped chaos. The refractory period ensures one-way organized traffic of nerve impulses. Technical analogy. It's like a reset button that prevents double clicks, stopping the neuron from sending false or duplicate signals. This built-in safeguard keeps your nervous system reliable so you don't misfire when reacting to rapid changes in your environment. Not all nerve signals travel at the same speed. Some need to get there fast like messages to pull your hand off a hot stove. Enter the myelin sheath. Myelin is a fatty layer that wraps around axons, acting as electrical insulation. Technical term, saltatory conduction. Instead of crawling, the impulse leaps from one node to the next. These nodes of Ranvier are like stepping stones, allowing the signal to jump quickly, skipping over insulated sections. Let me tell you a story. Ever notice how some people react instantly to pain, while others take a moment? Often, it's due to the amount of myelin on their neurons. So, thanks to myelin and saltatory conduction, your nervous system delivers express messages vital for survival and sharp reflexes. Now, let's connect the dots. When you touch something hot, sensory neurons fire, sending action potentials to your spinal cord relay station for signals. Interneurons process the incoming data and decide on the right response. Motor neurons then carry the command out to your muscles, telling them to contract. Technical terms here: afferent pathways, sensory in, and afferent pathways, motor out. Think of them as inbound and outbound mail routes. You might be wondering, is my brain involved in every reflex? Sometimes yes, sometimes no. Some reflexes are so fast, they bypass the brain entirely for speed. This entire loop from sensation to reaction shows how action potentials are the digital language that keeps you safe and responsive in a fast-moving world. Let's wrap up by considering the big picture. Each action potential is like a digital 1 or 0, but together they create complex patterns, your brain's own Morse code. What's truly fascinating is that your brain doesn't just count signals, it interprets them based on frequency and origin. For example, a rapid series from your ear means a loud sound, while a steady pattern from your eyes means steady light. Technical terms: temporal coding, timing of signals, and spatial coding, location of signals. Picture an orchestra, with each instrument playing its part in perfect harmony. Now, you might be asking, can my brain really understand all this digital chatter? Absolutely. It's decoding billions of impulses every second. So next time you catch a ball, dance to music, or react to danger, remember it's all thanks to the genius of your neurons, firing in a language only your brain can speak.